So my name is Caleb Whittier. I am a PhD student in the Department of Material Science and Engineering.
And my name is Joaquin Reyes. I'm also a PhD student in the Material Science and Engineering department.
And today we are going to talk to you about some advanced STEM EELS analysis that you can do with the Nion HERMES that we have here at McMaster University. So to give a little bit of context as to why the Nion is so special, through the past several decades, they have been making some progress in improving the energy resolution that you can get out of your transmission electron microscopes. So several decades ago, you were getting around in the range of tens to even 100 electron volt energy resolution. But as the years were progressing, in order to get this really fine spectroscopic information about materials, they were working to improve the systems, to work on the monochrometers, to work on the instrumental design, to really get this fine information on the nanoscale, because that's what the transmission electron microscopes are very often used for, to get this fine information on the nanoscale or even atomic level information. So this has taken many years of progress where it's very slowly progressed over. In the early 2000s, they were starting to get around the improvement towards the tens pretty stably. But then more recently, in about 2020, it was shown you could get sub 10 electron volt energy resolution. Now, the amazing thing about getting sub 10 electron volt energy resolution is that once you get down to this level, well, then you can do really fine kind of spectroscopic information on all kinds of systems. You're not limited to just doing chemical analysis. You're able to do some very unique science that we'll be talking about a little bit later to show how interesting our Nion HERMES is, for instance. This is one of the results that we are able to get on our scope. We're able to get a 3.7 electron volt energy resolution out of it. In fact, we can even push this to about 3.2 electron volts if we say really fine tune our settings in the microscope. It just takes a bit of more work. So it's not the easiest thing to do. It's taken many decades to get to this point, but now we're at a point to do some very interesting science. So in order to understand how we actually do this, we need to think about what the instrument is actually bringing to the table to accomplish this. Well, the first thing that you will notice about the Nion HERMES versus your most typical TEM is that it's an inverted design. Typically, your electron gun for a TEM is going to be positioned at the top. In the Nion HERMES, it's an inverted design, so it's completely flipped. So instead, you have your electron gun positioned at the bottom. So now your electrons are propagating from bottom to top. This is done just to improve the mechanical stability of the system. The electron gun is very heavy, so if you put it at the bottom, you have a very mechanically stable system. This reduces vibrations as a whole throughout the system. You also have an ultra-high vacuum instrument. So this is an order of magnitude higher vacuum than is typically encountered in TEMs. This helps with keeping the system clean, with improving, with reducing contamination throughout the entire scope. So it means that there's going to be some greater considerations for prepping your samples, putting your samples into the scope, and with working with it. There's a little bit of more learning required in that aspect. Now, if we're going to look at the specific optical elements that are very interesting for it, at the very bottom where we have our electron gun, well, our electron gun is a cold field emission gun. So this is a very bright, this gives a very bright beam with a very narrow energy spread. So this allows us to do some very fine analysis just as is. But to improve how good that beam really is, we take it and we pass it up through this monochromator. This monochromator takes the beam, kind of narrows down that energy spread and takes out some of those chromatic aberrations. And then it puts it through our condenser system, passes it through a C3, C5 corrector, which corrects for some of those geometric aberrations that are present in the probe. And then your sample impinges on your sample. So at the sample plane, this isn't the most interesting part of the scope necessarily, but I personally think it's very cool because you don't see it in many TEMs, but you have a pole piece camera. So you just have a camera at this plane so you can see where your sample is relative to the pole piece of your scope. It's not the most groundbreaking necessarily, but it's cool in my thoughts. You then pass up through the projector system, through the detectors, and through the quadrupole optical coupling module. This coupling module is just serving the role of coupling from your projectors into your spectrometer. It also helps with dealing with some of those higher order EELS aberrations. And then once you pass through your detector plane and your coupling module, you enter into your spectrometer. This spectrometer is where you handle all of those other EELS aberrations and where you can actually do all of that advanced spectroscopy work. At the end of it, we have a very specialized EELS detector, which we will be talking about a bit later. And just as a point for something that's coming a bit later this year, we will be having a cryo holder coming soon, which we will be using to study, say, beam sensitive materials or to study quantum materials whose properties are most aptly studied at these lower temperatures. Now, some of these aspects do require a bit more focus on them because they're really the selling points of the instrument. They're really important. One of them is the monochromator. The monochromator design for the Nion is very different from how you would see it in a lot of other TEMs. So in the Nion microscopes, the monochromator is based entirely off of a magnetic dispersion system. Typically, you would see a mono designed based off of decelerating and then reaccelerating the beam. The Nion does not follow that at all. Instead, you just use a series of magnetic lenses to first take your beam, deflect it into your series of magnetic lenses, deflect it again, deflect it, and then deflect it again. So what's actually happening here is we are bringing our beam in, it's getting deflected at our first two lenses, these two guys here, where it gets deflected in this prism, and then we're essentially dispersing it and redispersing it in series. And then the second half of here is just the mirror plane of this ray diagram here. Inside of this monochromator, we have a series of sextupoles as well that are positioned at the start and the end of our monochromator. These are just to help with some of the lower order aberrations that are induced by these magnetic lenses, but we can handle the higher order aberrations using our C3, C5 corrector that's a bit further down the line. Now this C3, C5 corrector, the important thing about this monochromator is that when we start here, we're at 300 millielectron volts, about 250, 300 millielectron volts when we enter the monochromator. When we go through this series of dispersions and we exit the monochromator, we can get down to about 5 millielectron volts, 5, 6, pretty easily. if we do a bit further tweaking, we can get this down to that 3.2 that I mentioned earlier. The 5 is pretty much the easy baseline that we go for, but you can get it a bit further if you really want to try and push it. You just need to really lower the amount of current that you're getting out is the one downside. But those higher order aberrations that I mentioned, these are handled by that C3, C5 corrector. This corrector is just a series of quadrupoles and octupoles that are arranged in series. So you have a few different segments of quadrupole and octupoles kind of coupled together that will take your off-axis beams and just kind of do their best to shove them back on axis. You're taking those geometric aberrations and you're doing your best to force them to reduce. The important part about this specific corrector is that it's allowing you to correct these fourth and fifth order aberrations. Very typically, you're going to see that in TEMs and stems, the fifth order aberrations are going to be set in the factory. And then you're going to receive your TEM and you won't be able to adjust those fifth order aberrations. You will be able to correct up to the fourth, maybe every few months or so, but those fifth will be just set. The only people who can touch those are service, and they will not touch them really because those fifth are normally just set in stone. This C3, C5 corrector allows us to actually adjust these fifth order aberrations. We typically don't have to. They're very, very stable for months on end, but we will have to touch them up perhaps once, maybe twice a year, just in case of little bits of drifting over time, in case there's some kind of large instrumental error. It's something that we don't need to do often, but it's just to maintain that very high performance. By adjusting these, we make sure that our total geometric aberrations are only limited by seventh order. So we can get these very nice probes out of our scope. This is very important when we're working at the lower accelerating voltages especially, because these are going to get just distorted very, very easily. 30 kV, 60 kV, 100 kV, which our scope is aligned at, that any small amount of distortion in your probe is going to make it very difficult to do analysis there. This corrector specifically is allowing us to really do some high-end analysis at these kPs. For our corrector specifically, if we are using this to do some probe correction at 60 kV, we're able to get a ronchogram that gives us a very wide area that is just flat and aberration free. So we've drawn a little circle here that is approximately where we would insert our aperture. This is where we would actually be collecting data from. And you can see that we actually have a little bit of area outside of there that's still flat and remains aberration free. We still have a bit of area before we become aberration limited. So it's giving us very nice performance at 60 kV. And just to say what can we actually use all of this for? Well, the power of this isn't just the corrector. It's not just the monochromator. It's when we combine all of this together. If we have a CFEG, cold field emission good, that's already great. It already gives great energy resolution. 250 millielectron volts would be very, very nice in a lot of instruments. But if you add the monochromator on top of it, you're getting very easily 10 or less millielectron volt energy resolution. You're already doing great. If you have the C3, C5 corrector, you're getting great spatial resolution no matter what. If you take these and you put them together, then you have really opened the door to do a lot of very fine analysis. You're now getting the very high spatial resolution from that corrector, and you're getting that really fine energy resolution out of your gun and monochromator. So it's really by combining these two aspects that we're able to do this very advanced, very unique STEM analysis. So it's giving us both this high spatial and this high energy resolution out of our instrumentation. To go over some of the technical details as to what we get out of our scope in terms of spatial resolution, well, it's very good. At 30 kilo electron volts, we're getting around 1.2 angstrom resolution. That's very, very nice. Typically, you're going to be limited to a lot of the thinner materials at 30 kilo electron volts if you're trying to do imaging. That's the downside. But if you're trying to do spectroscopy on, say, non-intersecting geometries, or if you want to look at 2D materials, it's amazing. 1.2 angstroms is very good at 30 kV. At 60 kV, you can get about an angstrom, perhaps a little bit better, and you can still do some very nice imaging, some very good spectroscopy. And at 100 kV, you can get this about 0.7, 0.75 angstrom spatial resolution. You could probably push these a little bit further if you do some slight further tweaking, but these are already very good. These are about what you would need to get if you were pushing, say, 200 kV on other systems, just because of how good the corrector is on this system. As for what we are actually using this for, well, when we actually look at a real system, we can look at things like two-dimensional materials, so samples that are very, very thin, let's say 1 atom, 3 atoms, depending on how you define your 2D material. So you can look at something such as graphene, in which case that's our figure over here. That's graphene with some defects inside of it. Or you can look at a 2D material such as a two-dimensional transmission metal dichalcogenide. That was actually imaged here on our own system, but the sample came from a university in Korea. And this was also collected at 60 kilo electron volts, and it's giving very nice resolution here. Likewise, we can do some quantum materials. So materials that have very interesting properties for, say, quantum computing or for next generation optoelectronics, for instance. These are, this one on the left is also acquired here. It's coming from a professor here at McMaster, Graham Luke, but the image was acquired here in the CCEM. And the image on the right is a Komi superconductor from the literature. These are both still very excellent characterizations of the Nion. And if you want to go with a more kind of standard sample, something like a typical semiconductor that you would see, well, those are absolutely possible. You can do gallium nitride, which was actually this image on the left, which was actually acquired by Joaquin here. This is coming out of a University of Michigan group, the sample. You can do something such as a solar cell defect line. You can look at those grain boundaries and identify individual point defects within them, which was done by Quinton Ramas's group at the SuperSTEM lab. And you can even do just your standard kind of silicon sample, which we also acquired here at CCEM from Andy Knight's group. This is 100 kV. You can see those silicon dumbbells very, very clearly defined. It's a very nice image given. So if you have the corrector giving you this very nice, very fine image, very well defined. That's already great. It's good to have that in a STEM. But the question is, why are we doing all of this STEM analysis at the low KVs if we have something such as an instrument that can give us fantastic images at 300 KVs in other scopes, or fantastic images at 200 KVs in other scopes, because we can get slightly better resolution in those. Well, the important thing is that we're using this for STEM and we're using it for EELS. We're using it for STEM and spectroscopy. Now, the STEM is very good because it's giving us this nanoscale information, atomic scale information. But if we're working at very low accelerating voltages, then we are getting these very high inelastic scattering cross sections, meaning that we're going to essentially boost the strength of our EELS signals. This is very important for things that have weak scattering cross sections or weak EELS signals, such as, say, oftentimes you'll have weak phonon signals or weak plasmon signals, or you're looking at things that are typically obscured by the beam tail of your zero loss peak. And if you want to look at those with both the spatial and the energy resolution, something such as the Nion is very important to do that because it delivers that high spatial, high energy resolution. And to go over that EELS aspect and the spectroscopy side, I will pass it over to Joaquin.
Hello. So as Caleb already mentioned, the great benefit of working at low accelerating voltages comes from the increase in elastic scattering cross-sections, plus the capabilities that Nion offer on giving us a small probe with high energy resolution. But to further improve the capability of our EELS analysis in our instrument, we have an additional piece of instrumentation that is also very important, which is our detector, our EELS detector, which is the Detectris ELA. So Detectris ELA is a hybrid pixel detector that is made of a set of 8 silicon chips that are capable of collecting single electrons with continuous readouts. This is optimized for EELS, and the purpose of having single electron detection with continuous readout is to maximize the efficiency of collection when we're doing our experiments. Additionally, the system has zero dark signal and zero readout noise, which eliminates a lot of the noise coming from the instrument or from the detector when doing the measurements. All these characteristics allow for an excellent signal-to-noise ratio on the data, even if at fast acquisitions. So hybrid pixel detectors overall have shown a great performance in core loss EELS, and in particular, the ELA has further improved the quality of the data that you can acquire in this region. So here, for instance, we have an example of a barium strontium titanate interface over an LMSO substrate, where atomic resolution elemental core loss EELS was performed. And first, to direct your attention to the EELS spectrum, this would be the result of what is detected on the ELA. And you can see that we can have the zero loss peak with really high counts, and we can clearly identify different ionization edges that are not noisy. They are easily seen just by looking at the spectra. And they also allow for great signal-to-noise ratio in spectrum mapping or spectrum imaging. So for instance, here we have from left to right, the image coming from the zero loss peak, which results in an image similar to that of a Bragg field stem. And then we have the resulting positions of the titanium, barium, and lanthanum atoms extracted by the background subtracted data of their ionization edges. And finally, we can observe the really high quality RGB picture where we can identify the atomic positions of all the elements that we extracted, very clearly defined and easily to interpret and then to associate with further other properties. And talking about these properties, this is the region where the ELA excels above almost every hybrid pixel detector. And of course, it's also because of the high energy resolution that we can achieve with the Nion. So if we go to the low loss region, we will typically want to extract information regarding the band gap, interband transitions, some excitonic and plasmonic behavior. So for instance, here I'm going to show a couple of examples from literature mainly. And for instance, here we have an experiment done on black phosphorus. So black phosphorus is a phosphorus allotrope, which is comprised of multiple atomic layers. And in this case, the experiment that we're observing is by using the small probe, locating it in different regions of the black phosphorus, so one in this side, one in this side, where the thickness of the material is different, to try to catch what is the behavior, how the behavior changes as a function of the amount of layers. And you can see that already in the raw data, it is clear that we can observe some peak, some signal coming from the material that is easily seen without any further processing, thanks to the capabilities of the ELA. Now, after doing some background subtraction and post-processing analysis, we can identify then the multiple phenomena occurring in this material, which is, well, for instance, we can observe the onset where we would locate the bandgap of the material. This material has a very narrow bandgap of 300 milli-electron volts, so in the mid-infrared range, which is only accessible with a high energy resolution that an instrument like Nion can provide. And then we can also observe some other type of excitation. So here we have two excitonic peaks and an interband transition forming. And in this particular case, you can see that we can see how sensitive it is to changes in the intensity as a function of the material thickness. Another example to show also the benefit of, in general, doing STEM EELS, which is exploring the spatial distribution of these kind of excitations, is coming from this work on an infrared plasmons. In this case, we're seeing here a nanorod that is a few hundreds of nanometers long and 50 nanometer cross-section of lanthanum-doped barium tin oxide. And by locating our small probe at different positions, it is possible to extract different EELS spectra coming from each of these positions. So the red one corresponding to the edge, to the face of the nanorod, and then the green and the blue ones located at different positions in the edges. And you can observe that we are able to, that the instrument is able to resolve very fine structure changes throughout the whole system. And to further push this, you can also do spectrum imaging and extract the spatial distribution of these kind of excitations. And so here, the three lines that you see are some integrated regions of energy filtered maps that you can see on your right, where we can observe the dipole plasmon mode and some other higher order modes and how they distribute over the nanorod, which is very important information that can then be exploited to develop devices for photonics and optoelectronic applications or for energy storage and conversion, among others. Going to a different kind of phenomena that we are now enabled to evaluate and study using the Nion HERMES. We can see infrared surface excitations. So these type of excitations are typically surface optical phonons and surface phonon and plasmon polaritons, which is the coupling of these excitations with light. So again, taking advantage of the low accelerating voltage and the high spatial resolution, it is possible to investigate, for instance, the confined phonon polariton modes on hexagonal boron nitride, as we can see here on the right. So in here, this is a series of experiments of spectra acquired at the vacuum in the proximity of the material and then going inside into the bulk system. And as you can see, we can the experiment reveals small changes in the structure of the optical phonons of the material and the phonon polaritons forming in the surface and then propagating throughout the whole layer. So in this case, it is possible to identify at least 3 excitations that are confined within a region of 25 milli-electron volts. So the high energy resolution that is achieved on Nion is what allows us to separate this signal and properly follow the behavior that they have throughout a structure. Another example of what we can do with spatially resolved STEM EELS is investigating your surface phonons of ionic material. So here we have the example of a magnesium oxide cube, where we can observe two different surface phonon polariton modes that are associated to the corners and the edge of the structure. So we can do that association of properties and structure. And in the bottom, you can see the EELS spectra associated to the edge here in green and to the corner here in red. By locating the probe and rastering for a period of time in that particular region. You can see two spectra. This is because this experiment consisted of locating the probe farther away from the sample to then explore how the coupling of these surface phonons with the electron changes as a function of the position of the beam. Now, all this information enables the development and understanding of processes that are then used for applications such as nanophotonics or optical computing. Now we can also do push the high spatial resolution of the Nion to that atomic resolved capability and explore phonon spectroscopy of bulk systems, so both optic and acoustic phonons, and also localized vibrations associated to impurities or structural features on the system. Here we have a great example, which is really exciting, which is having just a single silicon atom impurity in a graphene layer. So these type of experiments are also done using a slight different configuration of the optics in the EELS. So this is what is called dark field EELS, where the main beam, the direct beam, is displaced from the entrance aperture to be able to collect localized inelastic scattering signal. And here you can observe, so what happened is with a very small probe in the Armstrong level, sub-Armstrong level, by locating it in the silicon atom and then going towards the neighboring carbon atoms farther and farther away from the silicon, it is possible to extract the vibrational EELS, the phonon EELS, associated to the silicon atom and how it affects its neighboring atoms until it becomes more constant or bulk-like as we go further away. And as you can see, this kind of vibrational mode is really sensitive, that is confined to just a few atoms or atomic layers apart from the system, so that already at the 6th atom, the presence of the silicon seems not perceived by the last carbon atom. Some other working structural features in semiconductors, for instance, here we have silicon grain boundaries. So here we have the cases of an symmetric and an asymmetric silicon grain boundary. And again, exploiting the spatially resolved maps using STEM EELS, we can have these colorful maps where we can identify how the intensity of different phonon modes is distributed throughout the structure, and how some vibrational modes might be suppressed or enhanced depending on the system at these structural features that are common in most materials for applications and devices. So here we have these squares that are associated with the spectra that you see on the right. And as you can see, with the capabilities of the Nion microscope, it is possible to identify some intensity variations associated with these structural defects, and also red shifts or energy shifts of the vibrational frequency of the modes localized in the particular regions that we observe. So this map is actually given from, I believe, this region at 60 millielectron volts. All this information has been explored with other kind of spectroscopies, but with the lack of this high spatial resolution, where it is found that it is really key for developing and improving nanoscale technologies. So in particular, it helps to investigate and understand thermal management and energy conversion at the nanoscale. It also has provided and opened some possibilities for some quantum sensing applications. And in general, in materials and solid state physics areas, it reveals information regarding the scattering and transport phenomena. Now, moving on to some additional capabilities from more advanced EELS techniques, we have what is known as momentum resolved EELS. So momentum resolved EELS pushes these dark field EELS or off-axis EELS a little bit further into efficient methods. And it consists on displacing the typical round EELS entrance aperture that you will have on an electron microscope for a rectangular slot aperture. This rectangular slot aperture will then select a desired direction in the reciprocal space in the diffraction pattern of a crystal. So for instance, here we have a portion of the diffraction pattern of hexagonal boron nitride, and the rectangular aperture will be located, for instance, along this direction going from the direct beam to the 1, 1, minus 2, 0 diffraction spot, or maybe just to the 1, 0, 1, 0 family of planes, where we can observe then the dispersive behavior of fundamental excitations. So the way this happens is once we have our rectangular slot aperture aligned with the region we want to collect information, we have to do some adjustments of the optics of the microscope, and then we start a simultaneous collection of inelastic scattering at different momentum transfer vectors. So this allows to then unveil this dispersive behavior and create these really interesting maps that we can see here, which for the purposes of these for these images are associated to the phonons of hexagonal boron nitride. So you can see all these branches then can be associated with different phonon modes that exist on the crystal. And when we're doing these kind of experiments, we do sacrifice a little bit of the spatial resolution, but we're still in the nanometer range. So we are able to perform both spatially and momentum resolved EELS experiments with high energy resolution, which allows us to unveil phonons and also other fundamental excitations such as plasmons. And there's some hypothesis of even exploring magnons. And yeah, this technique is really powerful. It's one of the major achievements that has been done with the Nion, and currently it's been pushed to investigate materials in like higher energy ranges. It is also a very complicated technique to do, so it requires a bit of expertise development before starting to get these really nice data. And finally, moving to one additional application that we can do with the electron microscope is that of the organic materials. So since we now are able to reveal the infrared region of the electromagnetic spectrum with high spatial resolution, we can start to investigate the local response of molecular vibrations. This will help the organic chemistry communities to better resolve or better define the molecular structure of complex organic materials. So organic materials and scanning, well, electron microscopy in general is a bit of a challenge because of the effects that the electron beam can have on damaging the structures. However, the Nion has a great platform to perform these kind of experiments, since we are operating at lower accelerating voltages, which can reduce the electron beam damage. We can take benefit of locating our probe in aloof geometries to reduce the amount of electrons that are impinged in the material. And we can take advantage of, for instance, our soon-to-come cryogenic specimen holder, where we can reduce the temperature of the system to make it a bit more stable under the radiation dose that the electron is giving. So here, there's already been shown some advances. So for instance, here we have a guanine crystal suspended in a lazy carbon grid. And you can here see a representation of how the crystal would look like on like an atomic model. And this is actually an example of how an aloof experiment will be done. So you will have the crystal, and then you will have the electron beam at a certain distance in the proximity of the crystal, which will still show or reveal in the EELS spectra the infrared active modes, and yields to this result that you see on the black line to the right. And when comparing it to an FTIR experiment, which corresponds to the red spectrum in the bottom, we can see that there is a lot of agreement between what the EELS can give you and what the FTIR can give you. So FTIR has a higher energy resolution than what so far has been achieved with the electron microscope, but lacks the spatial resolution that the electron microscope gives us, which then makes like a very good complementary technique for the characterization of this kind of materials. And with this, we would like to finalize our talk. Thank for all the assistants that are here listening to what we have to say, for the CCEM for inviting us to give this talk. And yeah, we're happy to hear some questions.